This video covers chapter 7 of the book. It covers a number of miscellaneous topics that I thought were important to include before moving on to the tutorials in the second half of the book. Essentially, it'll give some further details on the tutorials. I'd like to explain some information on the software codes that I use and where you can get further information and downloads. And then there's a couple of sections which explain some aspects of modeling, covering basically the meshing, the building up the model and the analysis, and some of the problems you might encounter with these different aspects of modeling. First of all, I go through this in 3 parts. I'll give some further information on the codes, installation, and some further information on where you might look for details on getting started. I'll explain something that's quite important for finite element analysis, and that is the unit systems that you should be using. These have to be consistent, and I will explain this. And then finally, I'll move on to these topics of some guidelines for meshing, modeling, and analysis. At the end, there's a short wrap-up. I have given a brief description of each of the tutorials in part 2 of the book in the preamble. Here, I just want to explain or emphasize the softwares that I use for each of these. Essentially, the first 9 tutorials are using FreeCAD and Calculix. So FreeCAD we use to create the models, create the mesh, and then to write out the input data set for the Calculix finite element analysis. This is all done within FreeCAD. The results files from FreeCAD are then from Calculix are then available in FreeCAD, and we can do contour plots, for example. Occasionally, it is better to look at the post-processor created or available for Calculix that has been developed by the people who developed Calculix. This is called CGX. I do use it occasionally. The tutorials 10 and 11 are using FreeMat. I had hoped to be able to use Calculix for explicit finite element analysis, but this really didn't seem to work. So I used FreeMat, which is a variation of, or a clone, let's say, of MATLAB, and I programmed an explicit algorithm and used this to examine certain effects like time step and damping and so on. Tutorials 11 and 12 again use FreeCAD and Calculix. One of these, for example, does a transient thermal analysis. You can't look at the results, for example, in FreeCAD. You can create the model. You have to use the editor to make a few changes, but then you have to use the Calculix post-processor CGX. I will explain in a moment how you download all of these softwares. For tutorial 13, again, I use this FreeMat code for programming a very simple CFD code. There is an alternative to this that can be used called GUI Octave. Both of them basically use the same scripting language as MATLAB. And then lastly, I use FreeCAD again, which is linked to OpenFOAM for a CFD analysis. And in this case, we use another open source post-processing code called ParaView, which I will be demonstrating also in the tutorials that I've prepared after following these lectures. At the top here, I've given some links for comparing available CAD codes and FE codes. These links give a very complete list of commercial and open source codes that are available for both CAD and finite element analysis. And from these, essentially, if you want to go the route of using open source software, then there's two main possibilities, that is using FreeCAD with Calculix or using Solomi with code Aster. I selected FreeCAD and Calculix. I find it a very convenient set of softwares for creating models and doing quite complex finite element analyses. I have listed there the main points or the main advantages that I saw, which was that you have a seamless integration of the two codes, FreeCAD and Calculix. There's good meshing capabilities via two open source meshes that have been integrated, called Gmesh and NetGen. The post-processing is not great, and as I mentioned on the previous slide, sometimes it's better to use the Calculix post-process CGX. There are links to other softwares, in particular OpenFOAM. And regarding the Calculix finite element code, it does have a very wide-ranging list of capabilities: static analysis, dynamic analysis, nonlinear analysis. There's a very good library of elements and material models. Another advantage I saw was that the format is based on Abacus, so anybody using these codes does have the advantage of also seeing a little bit how Abacus could work. The documentation is reasonable, and as I've mentioned, there is quite a good post-processor, the CGX post-processor. But another valid alternative would be using Solomi and Code Aster. I did try this. I found it a little bit more difficult to create, build, and run models, and for that reason I chose the FreeCAD alternative. This just gives you some references. I'll leave you to look through this. There's some references where you can find further information on the installation for FreeCAD and Calculix. The next slide also shows this. There's also some links there for very good tutorials and videos. I'll leave you to look at that if you are interested. This is the main download page for FreeCAD and Calculix. If you do install FreeCAD, best as always to take the latest versions. It's available on Windows, Mac or Linux. I've always used the Windows version, and it's a very straightforward installation process, very standard. And just to be aware, if you do install FreeCAD, it does come with Calculix already integrated, so there's no extra software to install there. When we go on later to use the OpenFOAM code, the OpenFOAM solver for CFD analysis, this is a separate code that has to be linked to FreeCAD, and this is done via a so-called add-on. I will be doing a tutorial on this and showing how that installation works, and I have also included a tutorial in the book on that. You would normally be installing the standard versions, but it is possible also to get hold of the development versions, and you can see this here in the center of the page. I have done this myself in the past. It's fairly straightforward. Again, here's some further information on the Calculix code. If you're interested, you can get hold of the code separately. If you wanted to do this separate to the FreeCAD download, you can get hold of the documentation. Again, I'll leave you to look through that if you are interested. And then finally, other post-processors. There is, as I mentioned, this graphics CGX post-processor. There are two links there. On the next slide, I will show you how what I find is the best download for use on Windows. It is using this B-converged version. If you download that, install it, you will find when you sort of double click on the results files coming from a Calculix analysis, it will automatically start up this CGX post-processor. It's a little bit basic, let's say. The way it works, essentially, you get this window appear when it starts up. Then you have to click somewhere down here on just outside the box on the left, and it will open this sort of window. And in here you would activate something, for example, zoom to zoom in or out, animate to show a sort of sequence of pictures, different viewing angles. And for example, the data sets information is stored in here. If you clicked on this, which I'm showing here, you click on this and then you get maybe a set of results. These could be, for example, eigenmodes in a buckling or frequency analysis. You then click on this and then the next window opens and you say displacement, for example. And then you would have to go through to animate this one here in order to use the picture, to get the picture. It's fairly straightforward. I never read the manual myself. I just experimented, and you quickly gain a basic understanding how it works. There is another alternative, which is using ParaView. Now, ParaView is an open source post-processing code. You can download this from this website. Well, you can download it. You'll have to Google it and find it. It's not difficult. But this link I've given here is a link to a complete tutorial on how you could use FreeCAD Calculix and then create the results files from Calculix to read with ParaView. So this is an alternative. It's a very good post-processor. As I say, open source. It is certainly an interesting alternative to what I do, but up to now I've never tried this. And here is this website for downloading the B-converged version of post-processor for Calculix. You see it here. This is where you've got to go. You've got to use this link at the top. Then you come down to here, double click on this. You'll get a file, and then it's a fairly standard Windows installation process to install that software. This shows the structure of files in a FreeCAD and Calculix analysis. If you are building a model in FreeCAD, every time you do a save, the file or all the information will be stored to some input name that you give, and the file has the extension .fcstd, FreeCAD standard. This can be updated at any time. If you stop working and come back to it later and you open this file, then you can continue building the model. If you do an analysis, it will write out a .inp file. So this is the file that's written out by FreeCAD when doing a Calculix analysis. This file is in ASCII format, so you can read it and modify it. This file is a binary file. You cannot do anything there. Indeed, with this ASCII input file, for many of the analyses we don't do any edits here, but you will see in some of the tutorials in the book, and the first tutorial I do after these lectures, we can go in there and edit this file. We can, for example, add plasticity information for a material. Such information is not possible at the moment to define in FreeCAD, and it can be done in the .inp file. And this is easily done actually, because FreeCAD has its own editor which you can open and directly introduce the changes you want. So this then is the file which is read by Calculix for doing the finite element analysis. A successful analysis will then produce these files here, depending upon the type of analysis that's undertaken. This is the main file, which will store, for example, in a mechanical analysis, it will store all the deformations, stresses and strains and so on. But there can be additional files written. For example, the .dat file contains, if we're doing, for example, a frequency analysis or a buckling analysis, it will contain information on the eigenmodes. This file is in ASCII format, so we can edit it. And in fact, the version 19, the latest version of FreeCAD, will actually display this file as a part of the results files in FreeCAD. And you can open that file and have a look at the results without leaving FreeCAD. These additional two files are generated, for example, if you're doing a nonlinear analysis. This would be information on the convergence, and this would be information on the iterations performed. This results file then is read into FreeCAD here. And we can then, in FreeCAD, we can look at the various deformations, stresses and strains, contour plots and so on. It's also possible to open this file with the Calculix post-processor CGX. I do show it in some of the tutorials, and I will be showing it in one of the tutorials after these lectures. It has certain advantages, and indeed if you're doing something like a transient heat analysis, then you can only look at the results using this Calculix post-processor. I did show how to install this B-converged version of this post-processor on Windows. If you then double click on this file, this post-processor will automatically open. So I think it gives a brief overview of the structure. I'd like to move on now and just talk about consistent unit systems. These are important when doing a finite element analysis. It's important in any finite element analysis that you use consistent sets of units. So if we look, for example, at this relationship here, if we express the mass in kilograms and the acceleration is in millimeters and milliseconds, so acceleration is millimeters per millisecond squared, then the force will be in kilonewtons. If we built a model where you express things in kilograms, millimeters, milliseconds, but you express the forces somewhere in there in newtons, then this would be an inconsistent set of units, and it would lead to real problems. With this consistent set of units, you'll create or you'll generate results for stress in terms of gigapascals. But if it was inconsistent, then it would be very misleading what the stress is. You could do an analysis with inconsistent units. The finite element codes will run, but it would become very difficult to interpret the results. Have to be careful on that statement. It could be that you could get problems with round-off errors due to strange numbers, for example density, but generally it will run. There are many, or not many, but there are quite a number of different sets of consistent units that could be used, and I will show those on the next slide, or some of them on the next slide. It's a little bit confusing with FreeCAD in that it does, for example, have a database, and properties are stored within that database in certain units. I will also show this in a moment. You have to make sure that if you overwrite or modify slightly any numbers within that materials database, that you stick to the units that are shown there. Because what will happen is that the FreeCAD code will convert everything when it's creating the Calculix input file, and it converts everything to this set of units. They could have chosen a different set of consistent units, but the developers have selected this particular system of units. So the important thing is define things in FreeCAD using the unit systems that you see there. And it's a little bit unusual in FreeCAD that you always see the units to be defined. So for example, density might be in kilograms per meter cubed, then stick to that. But when it comes to writing out this input file, it will convert everything to these units. Here are some sets of consistent units. This is the one we use, or FreeCAD and Calculix uses when doing the analysis. But when building the model, you can use different sets of units. There will be conversions done to output everything to the input file in this unit system. And you can see other sets of units here that we could also use for a finite element analysis. I just want to repeat some of the points I've probably already mentioned. For example, up here is the typical panel from the materials database. This is the properties for Calculix steel, I think. But you can see here, for example, the density is 7,900 kilograms per meter cubed. So it does specify the units it's wanting to be using here. The Young's modulus is expressed in gigapascals, 210 gigapascals. And there are other units here or other properties for thermal analysis, and you can see the units. So if you want to change anything, it's possible. You would actually have to activate this tab here so that you can edit numbers, but then you could change it. But if you were using, for example, you want to modify this to be aluminium, you could click on here and change a number, and you could change that to 2,800 kilograms per meter cubed. So you can modify things, but stick to these units when doing the database or when modifying anything within the materials database or anywhere else in the code. Stick to these units. You will see these units being given, and then put in the appropriate numbers for those units. But when we come to write out the file to the input file used by Calculix, it will be expressed always in the units here, which I'd already shown you. Is this set of units also shown here? So, for example, if you were to look a little bit higher up in this data set, this is information at the bottom, but if you look a little bit higher up, you will find that the modulus has been changed from 210 gigapascals, and it's now expressed as 210,000 megapascals, because megapascals is the units of stress, which is the same units as modulus in this particular unit system. I hope that is not too confusing. I'm going to move on now and talk about some of the issues in analysis and modeling, and then just finally give a wrap up. First of all, I put together a few thoughts on meshing. It is important to try and get a good mesh. If you have very distorted elements, for example, this can cause problems. You can't expect good results from such elements, and You may also find that you run into problems when you come, for example, to solve the inversion of the stiffness matrix. Such elements can lead to problems. It is often almost impossible to avoid some distorted elements in a problem, but they shouldn't be excessive, and ideally they shouldn't be in the areas that are critical, meaning the areas where you're really looking for good results. FreeCAD does use this free meshing technique with either triangles for 2D problems or tetrahedra for 3D problems. This has the big advantage that it can quickly fix a mesh or construct a mesh for more or less any geometry, but it does have the disadvantage that you don't have very good control of the distribution of elements and the mesh densities in different regions. There are some tools in FreeCAD to help to control this, to specify locally on the edges or surfaces some mesh refinements, but generally it's a bit limited, let's say. In principle, what you're trying to do, if we think of a mechanical problem, what you're trying to do is have a fine mesh in areas of high stresses, and you can use a somewhat coarser mesh in areas of low stresses. Or more correctly, it's to say you're looking for a good mesh, a fine mesh in the areas where you have high stress gradients. The same applies if you're doing a field problem with flux. You'll need a fine mesh in areas where there's a lot of flow or gradients of flow taking place, and you can use a coarser mesh in other areas. Of course, with modern computers and fairly small problems, you could take the view that you just use a very fine mesh everywhere, but this is not usually very good practice, and you can quickly run into problems if you extend the analysis to look at nonlinear analysis, or you do parametric studies or some kind of an optimization of a structure which requires a lot of analyses. Then the computing time for a very fine meshed model could become excessive. You've got to make sure the meshing you use is suitable for the loads and boundary conditions that you want to apply. FreeCAD does not have mesh checking options, but a lot of the codes these days do have this. So, for example, you can usually do checks on the continuity of the mesh. That is, are all the nodes properly connected without gaps? Sometimes in complicated models, you'll have duplicated nodes or duplicated elements, and it's very difficult to see these, so there can be checks done to make sure there is no duplication. If there is duplication and you load the structure, for example, you will find gaps occurring. And there can be checks on the elements themselves, checking things like the aspect ratio of the elements. The length shouldn't be more than about 3 to 4 times the width, for example. Shell elements shouldn't have excessive warping, and generally the shapes of elements. So, for example, a triangle, an ideal triangle should have at each apex an angle of 60 degrees. It should be regular. And if it's very distorted, then this is not ideal, and you might want to think about remeshing. In the tutorials in the book, I didn't actually pay too much attention to the meshing, to be honest. I was more focused on the analyses methods. But in the tutorial I've done, which follows these lectures, tutorial 1, I do pay a bit more attention, and it does show actually some nice options within FreeCAD to finely mesh around critical areas in a notched example. So probably that's the best one to look at, that I've done at least regarding meshing. Some examples of different meshes are shown here. First of all, just to mention, if you can reduce a model and take advantage of symmetry, this can be beneficial. So, for example, a complete model is shown here, and if you've got symmetry in the loading, so we've got loading here, and essentially this boundary condition is a symmetry of the loading. There is a point here I should mention. This boundary condition would not be good in an analysis. One of these nodes should actually be fully constrained to stop rigid body motion in this direction. But even if this one node was fully constrained, you would have symmetry about this point, about this axis, and of course you've got geometric symmetry about this axis. So you could easily model a quarter model like this. In this case, these constraints, as I've drawn here, would stop any rigid body motions. There's some example of the meshing, different options here. This is really not a very good mesh. We'd expect stress concentrations in this region. We really want a much finer mesh here. And there's very poor grading between these elements and these elements. Also, there are some rather unfortunate elements in these regions. So I wouldn't regard that as a very good mesh. This is certainly a step in the right direction, but again there are some poor elements here, and again the grading between these zones is not particularly good. This would be a good mesh, albeit for the full structure. This I think I did with a particular preprocessor which allows to generate holes within a rectangle, and you can see a very nice mesh has been generated here. Quite a good transition between this zone and this zone. This sort of thing would be a bit difficult to do with FreeCAD, but you could generate things that would be reasonably comparable. These are a few other thoughts on the modeling that I've put together. First of all, getting the right elements. We would usually regard quads and solids, 2D quads and 3D solids, to be slightly better than using triangles and tetrahedras. However, I have to say the triangles and tetrahedras, the higher order triangles and tetrahedras in FreeCAD and Calculix are actually very good. So you shouldn't worry about using these. Generally, we would say that higher order elements, well, always higher order elements do give better accuracy, but do keep in mind they are computationally more expensive. You have far more degrees of freedom, the stiffness matrices are going to be much larger, and the inversion is going to be much more expensive. For implicit analysis, we usually always use higher order elements for the better results. However, for explicit analysis, where you're doing things like car crash or metal stamping, experience has shown with these types of analyses it's better to use lower order elements. So we're talking about elements which only have nodes at the corners or apex of triangles. We don't have mid-side nodes, but we use a finer mesh of such elements. These usually are computationally the best and will provide the best accuracy for computational cost. Be aware, if you are joining elements in a complicated structure, if you're joining different element types, do beware the degrees of freedom that each element type does have. For example, if you connected a beam having 6 degrees of freedom to a solid element to try and make some kind of a representation, this is possible, it's not a problem at all, but notice that only the translations will be connected. The solid element only has 3 degrees of freedom at each node. The translations will be connected, and such a joint would actually produce a pin joint. It will be free to rotate. Moments will not be translated from the beam to the solid. So do be aware of these sorts of issues if you're making up complicated structures. It can be difficult sometimes to select the right material models. For example, if you're trying to do nonlinear analysis involving failure, it can be very difficult to get failure properties. In field type problems, it can also be difficult to get properties. So, for example, some areas I've worked in recent years is fluid flow in fabrics. Trying to measure permeability of fabrics is actually a very difficult thing. There are no standard tests available for such measurements, so you can't really expect very reliable information. We can measure modulus and failure strains in a metal very easily, but some other things like permeability and conductivity in field problems can be much more difficult to measure. And inevitably, you might be forced to do some kind of a calibration between a test result that you might have and a simulation or analysis model. Do be aware if you can reduce a 3D problem to a 2D problem. This is relating back to the last slide, whether there's some kind of axis symmetry in the model that can help you to reduce the problem. I have used symmetry in a number of the tutorials in the book, and there's an interesting one in tutorial 11 if you do get the book, where it was an axisymmetric problem, but in order to set it up and to check all the things like contact and heat transfer, I used just how shall I say, a slice of the problem just to get it all working first before I moved on to the full 3D geometry. Application of loading, boundary conditions, especially in field problems, is not always straightforward. This is shown in tutorial 1 of the book, where I tried to analyze we analyze a simple unit cell of a fiber reinforced material. And you will see in that example, although you think you can set up symmetry boundary conditions, it's not always that straightforward. Finally, some points on the analysis. If the analysis fails or aborts for some particular reason, have a look first of all at the output listing. The output from Calculix is perhaps not so helpful on this, but most of the commercial codes will give very useful information on why an analysis has broken down. If the stiffness matrix, for example, fails to invert, check that you've got the necessary boundary conditions to stop all rigid body modes. If you get an error message, for example, with the Jacobian, this is often to do with a very distorted element somewhere in the structure that would have to be corrected. Sometimes, if you have a complicated model, it can be very useful just to temporarily take out certain options and see if the model runs again. This can be a way of trying to identify which option is perhaps giving you problems. This is often the case, for example, when you're doing something with contact. If an analysis goes wrong, you might want to try removing sophisticated material models and replace them with simpler ones just to see if it runs again and whether or not it is the particular material models that is causing problems. And in fact, very often what I do when I'm building a complicated model, I will check it runs, check the loading and boundary conditions by using simple material models before moving on to sophisticated ones. Always very useful to try and do a linear analysis before you move on and try a non-linear or dynamic analysis. Essentially, if the linear analysis doesn't produce sensible results, then you're not going to get a complicated non-linear or dynamic analysis to work. Some things you should check when you've got results. Have a look at the deformations. I do this in the tutorial following these lectures. I use a scaling factor on the deformations and have a look at how the structure deforms. This can be very useful to get an idea whether or not the deformations are sensible compared to what you expect regarding the boundary conditions and the applied loading. Have a look at some of the contours. Make sure that things like heat flow or stress are continuous, make some sense. You don't have locally some kind of spurious behavior due to some local effect that shouldn't take place. This second point here I've just mentioned actually about scaling the deformations to have a look if they are sensible concerning the loading and boundary conditions. In an implicit analysis, the applied or the reaction forces which are output to the output files in Calculix, you should check that these balance the applied loads, and if you're doing an explicit analysis, the energies should balance. In other words, the energy from external loading plus the energy from internal deformations, plasticity, should equal total energy and should be constant. This is something I go through in tutorial 11, where we program a simple spring element, and there is an exercise there on looking at the energy balance. Have a look at the results you've got and just check really that the mesh you're using for the analysis is really suitable for those results. It may be that you've got high stress gradients and yet you've only used a very coarse mesh in some region. You might want to go back and just improve the mesh so that can be better represented. There can, in rare cases, you might get some kind of lock-in phenomena take place, or more likely, especially if it's an explicit analysis, you might see this hourglassing taking place where you get a very strange sort of shape to the mesh. I do discuss this very briefly in lecture 2 regarding integration, but if you see these sorts of effects, then you're probably better off to either improve the mesh or to activate a different element type. There are usually in commercial codes at least elements that are less susceptible to locking effects or to hourglassing. I'd just like to emphasize here that the first 2 tutorials in the book really give a fairly detailed description of how to build a model and set it up for analysis. So I think it's important to go through those if you have the book. Otherwise, have a look at especially the first tutorial following these lectures, where I've done a YouTube video that gives a fairly detailed description of how to set up and do an analysis. And if you're interested in using the Calculix CGX post-processor, then there is a brief description on tutorial 6 in the book. Finally, things maybe I discussed in the book in a little bit more detail. I have given a bit more details perhaps on the different codes, and downloading and information on 2 of the codes I've rather jumped over here. In the book I go into a little bit more information on this FreeMat and GUI Octave codes, which are variations of MATLAB, open source. There's also some topics I discuss in a bit more detail: mesh dependency, and in particular challenges with nonlinear analysis, things you have to check when doing nonlinear analyses, and some more details perhaps on how to validate the model results compared to test results. Otherwise, I think that's all I would like to cover on this particular chapter 7. Following this, I do go through a set of 4 tutorials using FreeCAD, Calculix, and the last one using FreeCAD and OpenFoam, which I think you'll find useful, I hope. And in those tutorials, I do try to link the analyses and what sort of elements are used, for example, and how the analyses are conducted with the material I've been covering in these 7 chapters.